So today we are going to discuss whether it is actually possible to use some LLMs, already available LLMs, to classify astrophysical transients or not. Now you might be thinking, what is that? What are astrophysical transients and how can we use actually LLMs? So if you're in for it, let's lock in and we will discuss a very, very interesting paper. We're going to discuss astrophysical transients and how LLMs can actually help us to classify astrophysical transients. Let's go. So what are astrophysical transients? Astrophysical transients, a book definition is that when astrophysical objects change their brightness over a very short period of time, and this short period of time, it could vary from months, days, minutes, to over a period of 6 months, a year. Okay, so how do we actually think about transients? We think about taking images and taking difference of images over time and see whether there are any changes in the brightness of some pixels in those images. So let me take you to some examples in a paper. So let's say here we are in a paper where they clearly show current science image, that the one that you're seeing on the left, and then they are compared with some template image. Template image is, you think about a telescope, specifically a survey telescope, that will operate over a few years, 5 years, 10 years. It will take image of sky over time. When it starts operating, it will take the whole image of the sky, and that becomes the reference or the image that we would like to compare anything else with. So let's say this image was taken when the telescope started operating, and this is the current image. Let's say last night I took this image and I see this weird bright spot on the image. So what I do is I make the image difference from this image, from the reference image to the corresponding science image, and then what I get is the difference image. And I can clearly see on this difference image there's a big bright spot. And this, of course, is an example of an astrophysical transient. Now the brightness of this, how it will vary, it depends on the types of objects, whether it could be a AGN, active galactic nucleus, could be a tidal disruption event, could be a supernova event, depends how the brightness will vary. But you could think of this as something that will vary over a period of time, days, minutes to months. And we have these three different types of images. Once again, reference image, corresponding science image, we take the difference, and if there are some difference, let's say a small difference here, again, we have discovered an astrophysical transient. Something very explosive that's happening up there on the sky. We take images over a period of time, and we see that some pixels are brightening up or some pixels are dimming. It's not always that things are always brightening up like a supernova explosion. It could be that things are also could be dimming. So that should also show up in the difference image. Now, given this astrophysical transients, now we automatically think of, okay, so we have taken images over a period of time and we have discovered some astrophysical transients. Now the idea is that we could go on to do further analysis. What type of object it is? We could take, going from images, we could start taking spectra from that part of the sky, particularly from that object. Now, before we do that, we first make sure whether the difference that I'm seeing is actually an astrophysical transient or is it some fake event. Okay, so we have discovered something. But how do we actually know that this is an astrophysical transient and this is not some weird artifacts of maybe, let's say, a problem in the image difference scheme pipeline? There could be some other artifacts. The most common ones are some hit from cosmic rays that would create a weird flash on the pixels, and we think of that suddenly as, okay, or maybe confuse this as with a astrophysical transient. It's not, it's just a cosmic ray hit. Some other things, given that we have now too many satellites, specifically from Starlinks, there could be some trails on your image. And of course, you understand that if I take same parts of the sky, take the images over a period of time, specifically if there is a satellite that's moving, we're going to have this streaks, right? I guess you have all seen these beautiful images of 3i Atlas taken over a period of time. Anyway, so those are not astrophysical transients. Astrophysical transients, once again, are something like, let's say, a big supernova explosion. Could be something like a black hole mergers, and then there's a huge explosion, huge amount of energy release, and we discover them as astrophysical transients. So there is this big step before we do any type of further analysis. First, we need to make sure whether these transients, they're actually real or bogus. So this is a huge step in further analysis process. This you can think of as like a pre-processing step. Now, before we release this data to the whole public, to our collaborators who are using the telescope data, we first make sure that the images that we are releasing, they're actually real astrophysical transients and not some bogus events, because nobody wants to spend their time on analyzing this non-interesting bogus events. Now, that takes us to the second step. How do we actually know whether this image is actually a bogus event or it's actually a real astrophysical transient event? And that automatically leads us to some image analysis pipeline. You see where we are going? We started from astrophysics, now we are going to data analysis pipeline, and of course that will lead us to what's the aim of the channel, to include some AI algorithms. Now, for images, we have specifically deep neural nets, computer vision algorithms. So a large chunk of algorithms that are developed use convolutional neural network. You pass this 3 images, science image, the template image or the reference image, and the corresponding difference image. You pass all of these images. You tag them real or bogus, and then you hope that during the real-time data, when it comes in, the algorithm should be able to tell you very reliably which one is a real, possibly real transient event, and which one could be a bogus or a fake transient event. Now that works very nice. We have very, very well developed algorithm. But that kind of lacks one important step, and that is the interpretability of how we get to the final result. So let's say if I show some images to my astronomer friends, they will tell me, perfect explanation. This to me looks like a real transient event because of this, this, and this. This to me looks like a fake event or a bogus event because of this, this, and this. Now that is almost impossible from a convolutional neural net, from a deep network. We can always extract the features, and then we can go specifically, I guess people, whoever you are watching, I guess you do this kind of analysis. You go to feature space and then you reduce the dimension of feature space. Then you plot it as PCA, Principal Component Analysis, or TSNE, Stochastic Neighborhood Embedding. And then we see some clusterings. So let's see some examples of that. Right, so here what you're seeing are some examples. I will link the paper in the description section. I can also just show you right now the title of the paper. So this one actually analyzes images with convolutional neural net, so transient-optimized real-bogus classification with Bayesian convolutional neural net. So Bayesian networks, they're probabilistic networks, but you can check the paper by yourself. Let's get to this clustering part. What we're seeing is that when we have these different types of events that are getting classified by the network, we extracted the features just before the final layers, and then we are plotting. We do some dimension reduction with PCA or TSNE, or maybe with UMAP, some manifold learning techniques, and then we have this very nice 2D representation plot. Now, why do we do that? Because it's almost impossible to think of analyzing 512 or 1024 dimensional space. So what we do is we go from 512, 1024 to 2 dimensions so that we could plot something like this. We could also have 3D plots, but 2D plots are usually easy to visualize. So what you're seeing here are these different types of clusters. So something like, let's say, planets, this MPs, to some synthetic transients. Synthetic transients, by the way, create a separate clusters from the junks. This random junks, let's say, produce this red clusters that are completely segregated from the synthetic transients. So that's great. What's going on here is that not only we have a reliable classifier, but we could also see a representation of features in a simple manner that could help us to segregate between different clusters, different events. But I might also ask, okay, that is great, but still that doesn't tell me. This plot alone doesn't tell me what are, let's say, the thinking process of the network that were actually used. Of course, I can go to some very deep features, but they're very difficult to interpret, right? So now here comes the idea of the paper that we are going to discuss. So let's read the title of this paper. It's a paper published in Nature Astronomy, and the title says Textual Interpretation of Transient Image Classification from LLMs. So this is a complete new territory. Now, the idea is that whether it's possible that I have this black box, the neural net, whether it's actually possible that this neural net gives us some textual interpretation, just like my astronomer assistant friend, whether he or she will be able to tell me what are the thinking processes that she made to give me this label, whether this is a real event or this is a bogus event. Now, this paper, by the way, the primary author of the paper was actually my previous collaborator, so I'm very proud of this paper. Anyway, let's read few highlighted parts from the abstract. So this is what we actually discussed, what they mentioned here. Okay, so we could use CNN, convolutional neural network, effectively used for real bogus classification. However, their reliance on opaque is not transparent. We don't know exactly what type of things went in on those latent representation to distinguish different clusters. Reliance on opaque latent representation hinders interpretability. That's right. It's very difficult to interpret. Okay, we could see this clusters segregating from each other. They're reliable. Based on the labels, they work pretty well, but how can I interpret them? So here comes the result, which is really, really cool. Look at this. Only 15 examples and concise instructions. Google's LLM, Gemini, achieves 93% accuracy across dataset that spans a range of resolution and pixel scales. That is insane. So just to give you a brief what they have actually done, we will go through it right now. But just to tell you what's going on, it gave 15 examples to Google's LLM Gemini. Now Gemini, we have discussed in our previous video, what is a foundation model. So Gemini is actually a foundation model. It has capability of interpreting different modalities of data, not only text, but also images, audio, video, etc. So you pass this example images with corresponding descriptions with only 15 images, and then you pass some test data, and then Gemini achieves 93% accuracy. no training, no fine-tuning. This we call few-shot learning. Again, we discussed few-shot learning in the video before, so take a look at that. So that is quite cool. No fine-tuning, no training of a network. You just pass examples, 15 examples particularly in this case, and then during test time it predicts what's real and what's a fake transients with 93% accuracy. Here comes the final point. Furthermore, by generating textual descriptions of observed features, LLMs enable users to query classifications as if navigating an annotated catalog. So what does that mean? So let's say I have these images and some human being that actually went through those images and wrote some annotation why I classified this. So that's the idea of interpretability via an LLM. LLM enable users to query classifications as if navigation of an annotated catalog rather than deciphering abstract latent space. You see, that latent space, we had these two axes, which are these compressed dimensions. We call them L1, L2. It's very difficult to interpret what are those dimensions and what actually went in on the process of classifying these different clusters through the network. What if we could actually ask the network, hey, what was the step that you took to classify this image as a real or a fake transient? That is insanely cool. So let's start reading. So they start with wide field optical time domain surveys. So that's the idea of survey telescope. That's why we have this current image, corresponding template image, and then we make a difference to find whether there is an astrophysical transient or not. Time domain happening over time, 1 year, 2 years, 5 years, 10 years. Commonly employ a technique called difference imaging to identify flux changes. You see now, flux changes between a newly taken image and the reference image. And such methods produce a flood of transient candidates. They will contain real events, but also contain some bogus. Now, here they use dataset from different telescopes that have different resolution. So Mirlicht dataset with a telescope size of 0.65 or 0.7 meters, Pan-STARRS, almost 2 meter telescope, so the diameter is pretty big. Atlas, 0.5 meter telescope diameter. So Mirlicht dataset comprises of 3,200 candidates containing explosive transients and some bogus variable stars. Atlas dataset contains explosive transients and some bogus events, spurious detections. You can think of them as false positives. Pan-STARRS dataset includes 2,000 candidates but features a type of artifact called chip caps. So what are chip caps? So you think of telescopes, this big telescope, of course, let's say the iPhone or your Canon or Nikon camera, they will have CCD or CMOS sensors. So this telescope will also have very similar CCD or CMOS sensors, and it's very difficult to completely pack this whole diameter with the CCD or CMOS sensors. So there will be some gaps between the CCD chips. So that's called the chip gap. That would create some weird artifact that might be thought of as a transient. They're not transients, they're coming from this weird artifacts. So that's called the chip gap. So that's basically the data set. And let's go back to the image that I have just shown. So this is the image taken by these 3 different telescopes. And you could see this different resolution already. So here they mentioned same transients observed in 3 different surveys. First we start with Pan-STARRS, then with Mirlicht, and then with Atlas. So Pan-STARRS of course have the biggest diameter of them 3. Now Pan-STARRS will definitely, from the diameter we can make a guess that this will have the best resolution. Then comes Mirlicht, 0.65 meter, and then Atlas, 0.5 meter. So even if the image sizes are the same, all of them I think 100 by 100, yes, same sizes in pixels, but because of the resolution of pixels, they cover different regions of the sky. So it is the same transient observed through different telescopes. And you see, we have the current image, the science image, we have the template image by different telescopes, and then we take the corresponding difference images. And we see that this sizes, they appear different, and that's just because of the resolution of the telescopes. But they're pointing towards the same transient. Now, what they do is they create this dataset. They mention it here. Let me come back here. So they create this 15 annotated images with corresponding description for every telescopes. So in total, 45 examples, 15 examples for every telescopes, 15 annotated triplets per telescope. Each triplet consisted of a target image, reference image, and difference image. Now you all know what are they. And these were accompanied by descriptive text. So you have the descriptive text that are also going in. And these are easy to do in a foundation model because they're already have this capability to handle different modalities of data written by expert astronomers. So these are not some textual description generated by high schoolers. Okay, these text descriptions are proper text descriptions generated by professional astronomers. 15 examples were manually selected so that they cover various diaspora of transients, including fake events. Now it turned out that compared with the 15 triplet configuration, if they use only 12 transients as examples, the performance drops down only by 0.5%. If they go down to 6 examples, then it drops down to about 1.4%. So let's say from 93% best accuracy to 92%. If they use only 3 examples, you'd think that, okay, the examples are going down, maybe the performance would be dropping down to 50% or something. It's not. Even with only 3 examples, the performance decreases just by 7%. So from 93% to something like 85%. So still only with 3 examples with Gemini, you could achieve 85% real-time classification of real and bogus transient. And that is insane. That is amazing. How do they actually compare the performance of this LLM result? They actually ask the human astronomers to rate, okay, what Gemini is saying. Is that coherent or not? So first they check the results, whether it's a real or bogus transient, does that make sense or not? And then they go for the textual interpretation, and then they ask human astronomers, hey, what do you think about this explanation, whether they're correct or not? So the results are actually fascinating. By the way, this is the main image showed up in the Nature Astronomy paper. So we have these 3 different images going in, and then Gemini gives the explanation. Okay, the new image has a bright circular source at its center. In the reference image, there is no source at the center, but a galaxy can be seen on the left. The difference image shows a positive circular source, which is this one here, marked with this red circle. Would be expected for a real transient. Transient sources can occur on top of underlying galaxies. Very well possible, with some supernova, type 1, type 2, close to the center of the galaxy, we could have something like a tidal disruption event, etc. So transient sources can occur on top of underlying galaxies, such as supernova in a galaxy. Right, there is. Look at that. Therefore, this source is classified as real. That is amazing. Now, the results that they show is that a total of 200 randomly selected mirrored transients were evaluated by this panel of human astronomers with the following results. So, they set up a scale from 0 to 5 of this textual explanation from Gemini. 0, very terrible, it doesn't make no sense, the result is wrong, the interpretation from Gemini is completely out of the place. And then 5, it is perfect. The way Gemini describes the image and the way it describes the possibility whether this is a real or bogus transient, that perfectly matches of how I evaluate the image if I'm an expert astronomer. That would be a 5. So it turned out that transients were evaluated by a panel of astronomers. The mean coherence scores exceeded 4. That means it's extremely good, indicating that on average, explanation given by the LLM were perceived as highly accurate and meaningful. The distribution scores were heavily concentrated around 4 and 5. Wow! Notably for approximately 120 of 200. So that's 60% were complete agreement with human astronomers with a coherence score of 5. That is insane, and actually they show an example plot here. Here you see, that's the average coherence score. It remains to 5 up to till 120 images. That is insane, and then slowly drops down. But look at this, even till 150, we are above 4. That is insane. With only 15 of millilith images, you could classify 93% of images with proper textual interpretation. Now that is great. I guess we are getting close to the end of the video. They also highlight some drawbacks, and I think if you are like a master student writing your master thesis or first year PhD student working on your first poster presentation, first paper, you should always think of how can I really think about some of the drawbacks of my own analysis. I think this is very critical as you're embarking on this journey of scientific explorations. You should always think about what are the common pitfalls of my analysis. This is very necessary before somebody else points out some obvious drawbacks. You should be able to think about this. You should think about this. You should discuss this with your collaborators, with your guide, so they highlight some of the drawbacks of this. And I guess people who are working in this field, of course, you could already think about the biggest drawback. And before going into that, let's think about it. So let's say if I have a simple convolutional neural net, let's say 1 million parameters. But if I compare that with Gemini, with billions of parameters, 100 billion parameters, of course, during the test time, to parse this image, to get the corresponding textual interpretation, to get a corresponding level, that would take way long time. And one of the biggest telescopes currently that is operating right now is the Vera Rubin Observatory, LSST telescope. And that will produce millions of alerts per night. Now imagine passing these millions of alerts through this big model, big Gemini LLM. No, we will be in big trouble. We will not be able to label, but most importantly, we will assign a huge chunk of resource for a potentially easy task. Potentially easy task because we have well-developed convolutional neural network that could classify real and bogus events. Why this one is necessary? This one is a way of showing that we could use LLMs to come to potential interpretation. This one you can think of having an AI assistant by your side, right? And they highlight this drawback. By the way, you can go through the methods, you could go through exactly what they gave in within the text, etc., etc. Let's see some of the drawbacks here. They mention very specifically somewhere here. Let me see. Here. However, the practical deployment of LLMs for real-time astronomical surveys demand careful consideration of computational performance. Traditional CNN-based pipelines can process individual images in milliseconds on GPUs. Yeah, it would be impossible with big LLMs like this. And they mention the Vera Rubin Observatory, which would produce millions of alerts per night, and running LLM through a commercial API under this condition, of course, you have to use the Gemini and the Google API. At present, is impractical. But then they say that, of course, LLMs are kind of becoming small. We could have a very small LLM with 1 billion parameters, and maybe we could reach one day potentially million parameters compatible with some convolutional neural net that could help us doing this task. So that's a way to bypass this. That is very cool. Now think about compressing this big LLMs into small models and having this AI astronomer assistance by your side. Isn't that cool? I guess we have to end the video here because it's getting really long. I hope you find this information interesting. I will link all of the papers, including Vera Rubin Observatory website, in the description below. If you like this video, if you find the information useful, maybe you would like to subscribe, and I will keep posting. Stay tuned. Thank you, everybody.